Yeah, so as we have created this data set, the next thing that we will do is, can you scroll down a little bit, Gaurav? Yeah, so I see the structure of the data set. So the how many rows and how many columns is a very important code, df.shape shape, and this will come handy quite a bit of time. And if you add one so let's say if you want to only know the row number or only know the column number, you can also write df.shape within bracket one. Can you write that third bracket one? Yeah, and then you run that, you will get only the row number. Can you please run it? Okay, yeah, one means a second, zero, you will get the row number. So if you write zero, because in the Python, the count starts from zero. So if you write zero instead of one, yeah, you will get the row number. So if you write df.shape and within that, so anything, basically anything after that, if you write third bracket as I told before, stands for the location. So if this will basically give you the first input or the zeroth input. In this case, zero means basically the first I index. So you can get this yeah, df.shape within bracket and then run. So you will get both of them. So I can also get probably the sum of the variables. So df.sum will give you. Now understand that if it is a numeric variable, it will give a sum. But if it is a variable which is a string variable, basically it will join the strings, because a plus b joins, if a and b are categorical variable or string variable, it joins them. So I might not want that, I might not, so I can find out one particular column sum as well. So df.sum within column one, if I just write it down, so it is, this one is joining the whole thing row wise. So if you see 29.3, the next line 20 12, line number 12 there. So df.sum within bracket one is joining everything row wise. So if I check the data set, so this is row sums in the context of, if somebody have used R before, they will know this is row sums. If you go scroll up a little bit, so 29.23 that you are getting is basically, scroll up, basically 25 plus 4.23. And then there is another, so next entry is 26 plus 3.24. And next is 25 plus 3.98. Now you see, when I write df dollar sum and within bracket one, that means one means it is basically joining it row wise. It is not dropping the first row, and that's why, can you run once more? So first time when you ran, it was giving you a error, not error, it will give you a basically a signal that you are joining something which has string data in it as well. So I can do column sum also, I can do row sum also. Column sum I have already shown how to do it. It's df$sum. If I want to join row wise, I will get df$sum within bracket row. I can also find out the mean and standard deviation of the of this data set. So like df$mean will give you the mean, and I was getting the error before. Actually, I'm not sure it's version difference or not. In my thing, at least those things were coming. In Gaurav's computer, those signals are not coming. So anyway, so I can also find out, instead of doing it, I can also find out exactly which location. So df.iloc, this is a way to find out exact particular column based on the location. So Gaurav, have you covered df.iloc this thing in your presentation?
Yeah, I just told them a bit, just to inform them.
Yeah, so df.iloc, that means you are giving the location. Now you are saying that, okay, I am taking a subset of the data set df, and the subset will be given based on the location. So there is a comma. If you see in the third bracket, within the third bracket, there is a comma. Before the comma, you write which rows you want to take. After the comma, you write which columns you want to take. So here I am taking basically first, second and third column. So 0th column I am not taking. 0th column is the name. 1st column is the age. So age column I am taking, and rating column I am taking. That's why I have written 1 plus 2. I could have also written a list of range from 1 to 2, something like that. And I am taking all the rows. That's why I have just written a colon in front of the comma. So colon in front of comma means basically all the rows. I'm not choosing any particular row. And then I am taking the mean. So the subset of the data is creating 2 columns only, 1 and 2. This 1th column and 2th column. So it's not first and second. So column index number 1 and column index number 2, because name is column index number 0. So that index number 1 and index number 2 it is taking, and then doing the mean. Same way, if I change mean to STD, I get standard deviation. I can also get the overall description like mean, median, a little bit on that if I go for df.describe. And if I want to get also string data will not have any mean, median, but it will have a mode. So that will give me, please run here. So that will give me this count is 12, and you see that the there is top name is James. I think there are probably more than 1 James or something like that in the data set. No? Okay, so then this top James is how it is coming. I'm not sure, probably it's a random number selected, because all of them are frequency has 1. But if you have a data set by chance, can you convert in DF? Can you go up Gaurav, can you go up and just make and brace the last one, the last name, and the
Sir, you can take the remote control.
Yeah. Can you just let me?
Yeah, you have to. You have to click on remote.
Yeah, I requested it. Can you give me the?
Yeah, prove.
Yes, thank you. So let's say if I just change this one as Tom. So then it becomes 2 Toms, right? Because Tom is the highest one. I just run this once more so that I get the data set. So there are 2 Toms. Now, if I run this describe all this thing, I should have Tom here. So top means the mode. So I can get the mean, median, mode very quickly if I use this kind of a data. I can also get 25 percentile, 50 percentile. 50 percentile is also the median. 75 percentile, so interquartile range and etc. I can get out of it. So these are some of the things that we have learned before. I have also discussed about binomial distribution. So to do binomial distribution, to solve the problems of binomial distribution, if you remember, there was n, p, and r, or if you remember n, m, and p, we were talking about. That's how I wrote the equations. So based on that, we can calculate the binomial distribution. So for that, we need this spicy library. I'm not sure whether that is already installed in his computer or not, but I will quickly run and check. So if it is not installed, it's installed basically. If it is not installed, you have to make this one as a uncommented basically. So if you make it as a comment, as a code, and then run it. So this PIP through which you can install it. Anyway, so the spicy library is installed. If you by chance in your computer it is not installed, make it a code and then run. It will take some time in downloading it, but it will run. So spicy is a very common library which is used for this various kinds of distributions and statistical analysis, basic statistical analysis. So what I do, in the spicy stats package, I am importing binom, this particular function name I am importing. So what is this function's job? This function gives you the binomial distributions corresponding values. For example, I have chosen n, p, and r. N is the number of trials, p is the probability of success in the trial, and r is the stochastic term. You are asking how many, what is the probability that there will be 4 number of trials. So you write print binom PMF stands for probability mass function. So that means the probability at that particular point only. And once I run it, automatically it gives me 0.11. So I do not have to do all those calculations. The same thing if I want to get the CDF, the cumulative means addition of all the probabilities up to that point. Cumulative density function, or in this case, distribution function. Cumulative, it's a categorical variable. So it should be cumulative distribution function. So that is basically 0.166. This is what? This is basically probability r is equal to 0, plus probability r is equal to 1, plus probability r is equal to 2, plus probability r is equal to 3, plus probability r is equal to 4. All things together, you get this thing. So if I can basically create, if this is given, all the problems that we were trying to solve yesterday from this thing, you do not need a calculator, you do not need to solve it. You can solve it in your hand or by codes itself. One important thing that we also do in binom, so let's say I want the range, I want the probability for all the values between, let's say 0 to, in this case, 10, right? So all the values between 0 to 10, I want you to create the probability of that. So what will I do? Let's say here I'm just printing the mean and variance. Mean is NP. Remember, n into p is the mean, and variance is n into p into 1 minus p. So that I'm printing it here. After that, what I'm creating a list of which range n plus 1. N is 10. That means range 11. Let me just write it down what I'm getting here. Just 1 minute. So what is range 11? Range 11 means 0. So anything between 0 to 11. So if I create a list of out of it, list of range 11, that will create a list 0, 1, 2, 3, 4, 5, 6. So 11 items starting from 0, ending at 10. Now these I'm putting as R values. I'm saving it here. Then what I'm doing this is equal to this particular probability for R in R values. So I'm writing a loop. So it's a for loop. So for R in R values, this is equal to this particular thing. And then I'm putting that within a array. So what I'm getting is a array of numbers where each number is basically the probability and the value of R gets changed. And then I'm printing the distribution. So if I run this, I'm getting, this is my probability. So 0.00140 and so on and so on. It goes on. And so if I rather plotted it, this particular distribution, you have learned how to plot, you will get a binomial kind of distribution, which looks like more of a it goes up and then goes down slowly. I can also randomly select numbers which comes from a distribution. This becomes very handy when you run a simulation. At a later point of time, we will do simulation, and or you will probably do simulation. For any kind of Monte Carlo simulation, you have to create variables, you have to create observations which follow a particular distribution. So to do that, to follow that, you have to basically you have to check this. So from NumPy, import random. So I'm using a random function. And random can be of different types. Random dot binomial, random dot Poisson, I will tell you. So in random dot binomial, my n is 10, number of trials are 10. The success of each trial is 0.6. And I am asking you, now if this has been told to you, give me 10 values, 10 random values which follows this binomial distribution. So these are what values? These are basically the values that you are getting. So I am asking him to give me a value which is between 0 to 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of these 10, 11 values, any value will be chosen. And what will be the probability of choosing each of these values? These are the probability. The probability of 1 being chosen is this much. 0 being chosen is this much. Probability of 1 being chosen is this much. Probability of 2 being chosen is this much, and so on. So that's how these values are getting chosen. Now I am asking, make these choices not once. So one time they are choosing and they got a choice of 8. I'm saying that no, don't do this choice once. Do this choice 10 times. So first time it choose 10, 8. Second time it choose 7. Third time it choose 3, and so on. So these are the 10 randomly selected random choices or random samples from a distribution. So those who have studied statistics before, if I keep on doing this activity, instead of size equal to 10, if I do size is equal to 100 or size is equal to 1000, and then take a mean of this array, what value will I get? It's a question to everybody. So let's say I'm keep on taking the samples. I'm keeping on taking the samples, and then I'm finding out the sample mean. What value will I get if the sample size is why 5, William? What is your idea? Why do you say 5? So let's just write it down. Let's say A is equal to, instead of this, I write it this. And then I write A dot mean. So what value will this be? Check. Let's check it. So A dot mean will have this. So it's not defined in. Okay. So let's do you want me to make it bigger? Let's make it further bigger. I'm not sure whether it will run. Memory error. Yes. So it will give some result. Just 1 minute. Oh, I made it too big probably. You see, it's close to 6. Any reason why? Why it is getting close to 6? Let's say I'm doing one more time. You see, it is very close to 6. Anybody want to say why it is coming very close to 6? What I'm exactly doing here?
The highest probability is for 6.25.
Come again?
The highest probability is for 6 here, assigned to 6.25. So basically, the binomial distribution, the
No,
probability
this is basically the expected value. So if I if I keep on running it, what is the value that I expect to come most commonly? That value is
NP.
this value.
NP.
That's NP exactly. So those who know central limit theorem, I will talk about that today, just now in another sometime. You will know that the population mean, which is 6, and the mean of the sample means, or a mean of a very large sample, let's say, will follow the same value. Anyway, so I was not about to show this, rather I was about to show this much. So this is how you can take a random sample basically. This will come in handy later. The same thing when I try to do in Poisson distribution, I import Poisson. The mu is 47.35, Sachin score I was talking about. What is the probability that Sachin will exactly score 49? This is the probability mass function. The exactly scoring 49 probability is 0.05, which is very low. But what is the probability that Sachin will score up to 49, which is CDF? Okay, so smaller than equal to 49, which will be a significant probability, which is 0.63. Again, I can also create a random Poisson with lambda is equal to 2 and size is equal to 10. So when the lambda is 2, or let's say lambda is 47.35 and size is 10. So I'm basically asking that give me 10 possible or 10 random values from Sachin's distribution, that what will be the Sachin score in the next 10 matches. So these are basically some values. There are some predicted values or some sampled values from that distribution. 53, 48, 38, 48, something like that Sachin will score in the next 10 matches probably. We can also do normal distribution, but before we go ahead with normal distribution, let me share my screen and show what normal distribution is. So, Gaurav, you can stop sharing your screen.
Your screen is visible.
No, you can stop sharing. Yeah. So I will share my screen now. Just 1 minute. So let us discuss about normal distribution a little bit, and then we will go ahead and see the codes of normal distribution that has been written there. So normal distribution is the first continuous distribution that we are going to study. Yeah. So normal distribution looks like this. This is the mean. And in this direction, we plot not probability, but frequency. So why do we not plot probability in binomial distribution? We were plotting probability. If I plot binomial distribution, this will be the probability scores like this. These are all bar charts and it looks like this. That's for a binomial distribution. This can be plotted because in binomial distribution, each of the observations like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in a 1 to 10 trial, each of these observations has some probability. But in continuous distribution, any single point has no probability or zero probability. So let's say, what is the probability that today at this particular time period, at this particular point of time at exactly at 7:30 p.m. the temperature of my room will be let's say 30 degrees centigrade. Now you see the probability that temperature at 7:30 p.m. will be 30 degrees centigrade is basically probability number of times this happens divided by number of times, anything can happen. Basically, temperature at 7:30 p.m. is any temperature. Now, whatever be the case here, this is infinite. So this value will always be 0. That is a problem. There is a fallacy or problem in the case of any continuous distribution, that a single point will have always a probability of 0. Now, if a single point has a probability of 0, I cannot plot a probability in the x-axis. So what I rather plot, sorry, y-axis, what I rather plot is only the numerator. So only the number of times temperature at 7:30 p.m. you got as 30 degrees centigrade. I am only plotting this much. I'm not even plotting the denominator part in this particular thing. So that's how we create this distribution. Now, there are certain characteristics in normal distribution. Normal distribution is continuous. It ranges from minus infinite to plus infinite. This is the range. What is the range of binomial distribution? Can you tell me? What is the range of binomial distribution?
0 to n.
0 to number of trials, exactly. And what is the range for Poisson distribution?
0 to
It's up to infinity.
0 up to infinite, exactly. So here this one is from 0 to so minus infinite to plus infinite. Okay. Then comes the next one, which is the mean, the median, and the mode of the random variable are at a single point. So that means what? If the mean is same, mean is in a single point, that means whatever it looks like in this side and whatever it looks like in this side is same. Similarly, if the median is at the same point, that means exactly 50% of the observations are here and exactly 50% of the observations the other side. So the median is, then the mean and median is basically at the middle point, and whatever is the distribution in the left side and whatever is the distribution in the right side are exactly similar looking. And then comes the mode. So see, one problem is even this is the mean is in the same side. So if by chance the distribution look like this, that this is my frequency, and like this, let's say, something like this. This is my frequency. Even for that, the mean, median, and mode is in the same place. Even this kind of a view. It's symmetric. Symmetric means whatever is the left side, whatever is exactly the same thing in the right side. That means it's more or less mirror image of each at this particular line. So if it is mirror image in the particular line, the center of gravity will fall in this particular line. And it's also the median. And at this particular point, the frequency is highest. So it is also the mode. So this one also and this one also will also both follow the same kind of this thing. However, the problem is that this one does not vary from minus infinite to plus infinite. This has a finite distribution. This stops from here to here. The range is not infinite. So this will have some value, let's say minus a to plus a. So to have these two things happening, these three things happening basically together, it has to have a bell kind of shape. It could have been like this also. Even then the median and mean are in the same space, but not the mode. The mode is here and here. So only this shape makes sure And this same and this minus infinity plus infinite make sure that it will take a bell kind of a shape. So these are some of the characteristics that we are getting. What other characteristics that we are getting? We are also getting another characteristic, which is the distributions probability. It has been seen that the equation is such, I'm not asking you to remember the equation, that if the mean of these things is mu and the standard deviation is sigma, then it has been observed that with that particular equation of this form of this bell curve, within mu minus sigma and mu plus sigma in this range, it has been seen 66% of your observation will fall. So the CDF, the cumulative distribution from mu minus sigma to mu plus sigma is 0.66 or close to that. The same thing, it has also been seen that the moment I do it mu minus 1.96 sigma to mu plus 1.96 sigma, the CDF, that means the distribution, this probability area is 95%. It has also been seen that if I further increase my sigma level, mu minus 3 sigma, this is almost 2 sigma. So next is mu minus 3 sigma, 2 mu plus 3 sigma. In this range, 0.9997, 99.97 will fall. And if I make it 6 sigma by any chance, basically 0.999997 will fall. So basically outside it, outside this range, 3 in 1 million will fall, will be outside. So this is because of this characteristic, this particular distribution is also used for a quality measurement. We call it 6 sigma quality. What does it mean? Let's say I am saying that I make nut bolts for a particular, let's say, aeroplane. And my nut bolts are exactly by design. The mail told me that you make 5 centimeter or let's say 1.5 centimeter wide nut bolts. I say that, okay, I make 1.5 centimeter plus minus 0.05 centimeter with 6 sigma quality. Let's say I say that. What does that mean? That means basically that 1.5 is my mean and 1.5 minus 0.05, which is 1.45, and 1.5 plus 0.05, which is 1.55. This is my 0.999997, which means this is my 6 sigma. And this is also my 6 sigma. Then what is my sigma? My sigma is basically 0.05 divided by 6, something like that. What, 8? 3? Something like that. So this is my sigma, I am telling it. Now nobody will understand this, my sigma means what. So rather than saying that, I am trying to say that only 3 in 1 million bolts will fall outside 1.5 plus minus 0.05 centimeter. That's how we signal quality. So this becomes a very open. Now, some of these probabilities you know. If you have understood up to this point, can you tell me what is the probability of, what is the area under the curve, or what is the probability of this particular point, this area? Can anybody tell me? This red area, how much is that red area?
(33/2).
33 by 2?
Sorry,
33, 34 by 2. Why it is 34 by 2? Anybody who did not understand, please raise your hand. I want to see that whether somebody cannot understand why it is 34 by 2. Everybody understood? William, what is the probability? William, can you hear me? William, are you there? Can you write in the chat box at least? Yeah, William, what will be the area under the curve if I go from minus infinite to plus infinite, the whole thing under the curve? So you see, as I increased from mu minus sigma to mu plus sigma, then mu minus 2 sigma to mu plus 2 sigma, then mu plus 3 sigma to mu plus 3 sigma, then mu minus 6 sigma to mu plus 6 sigma. Slowly I increased. The probability increased 66%, 95%, 0.9997%, 0.999997%. So if I now go to mu minus infinite sigma to mu plus infinite sigma, what will be the area under the curve? What does your hunch say? %, yes, exactly. So the whole probability from minus infinite to plus infinite is 100%. So then, if that is the case, in the first picture, William, I'm asking you, the black shaded area, beyond that, how much percent is left? Beyond mu minus sigma and mu plus sigma, beyond these two scores, how much percentage of observations are left? Yes, 34%, exactly. 100. And that's why, because that is 34% and because it is symmetric, means whatever is there, whatever is here, exactly that much percentage is here. That because these two are symmetric, this is 34%. So for some of the probabilities, you can calculate. For mu minus sigma, mu minus 1.6, 1.96 sigma, 6 sigma, 3 sigma, you can calculate because you know that how much is within this range. But for some others, you might not be able to calculate it. So for that, you have to use, again, either if you are using a package, then either a book, or you have to, there are certain statistics book at the end of that, these are available, or you have to use certain library. So first, what I call is this spicy.stats. Within that, the norm thing is there. I am calling it. So within norm, I am seeing PDF. So PDF has 3 entries. The X, the 0, the mean value. So this is the mean value and this is the standard deviation value. So PDF gives me the exact probability, not probability, the frequency at this point, the height. So if I try to run PDF gives me, it's not probability, it's basically this height. Let's say if this is this thing, let's say the mean is something, mean is 0, and let's say standard deviation is 1. And I'm asking you what is the height here in this particular point, just the height, not the probability. It's called the frequency. So height at 0.3, let's say, or minus 0.3. So that I can get from this PDF function. So the first entry is, let's say, minus 0.3 and then 0,1. If I run it, I don't know what happened to my system, but it will give you, if you run PDF, it will give you that particular value. Now CDF, on the other hand, will give you the net cumulative probability up to a point. So for example, in this case, if I wrote, okay, so I got this value. In this case, I wrote C 0, 0, 1. That means the mean is 0, standard deviation is 1, and I am asking him to give me the CDF up to 0. That means I'm asking him, if the mean is 0, and standard deviation is 1, I am asking this particular thing that give me the probability up to this point. So up to this point means what? Up to median. And up to median, what will be the CDF? It's 50%. Half of the people are below or exactly equal to this value. So that's why I'm getting 0.5. Can anybody tell me what should I write here to get, let's say, 0.975? What should be the value here to get here 0.975? So if a normal distribution has mean 0 and standard deviation 1, up to what point the cumulative probability will be 0.975? That means beyond that, only 0.025 number of observations or 2.5% observations will be beyond that point.
2 sigma, so basically on the right.
Yes. So it's almost, its exact value is 1.96. Okay. So if I run this, it should come 0.975. Yeah. Now I can also create, similar to before, I can also create random variables. Location is equal to 0. That means basically the it's a Gaussian. So the mean is equal to 0, you can say, and scale is equal to 1 means the standard deviation is equal to 1, and size is equal to 10 means I am getting 10 observations. So you can also create random normal variables, random normal sample using this particular formula. So where can we use this particular problem? So can I show you some, let's say, let me show you so yesterday I have shared one file, right? In this particular thing, in day 2 under session 3, there will be these problems. There was one problem that was left, we did not solve. Let's try to solve it. Yeah. So the last problem, the 5th problem, can you check? A group of students at a school takes a history test. The distribution is normal with a mean 25 and a standard deviation 4. Everyone who scores in the top 82.5% of the distribution gets a certificate. What is the lowest score someone can get and still earn a certificate? What I am asking you, basically, I'm asking you that, okay, there is this thing with mean 0. There is a normal distribution. It's not mean 0. Mean is how much? Mean is 25 and standard deviation is 4. The mean is 25 and the standard deviation is 4. You're saying that everyone who scores in top 82.5% of the distribution gets a certificate. So how much top 82.5% will come in the right side or in the left side? Can you tell me? So the top percentage, that means this many will be like that, or this many will be like that. Which particular picture is better, rightly explaining when I'm saying top 82.5%? That means this area is 82.5. Which picture is correct? Which of these pictures are correct?
The second one, like this.
Why do you think the second one is correct?
Because the higher numbers towards the outlier higher numbers should be towards the right, and they should be included, whereas I think lower outliers would be the ones who would not make.
Okay, so outlier is not the reason. Anything else that anybody else want to say?
So basically, they are saying top 82.5. So second picture demonstrates the 82.5 shaded area.
How do you say that? Why not?
Means so numbers are increasing as we go on right, and a top 82.5 will fall on the right hand side of this.
Yes. So the basic explanation is this is your top 50%. So top 80 to 5% will have higher area than this, not lower. Okay, got it. What I'm trying to say. If this is 25, this is normal distribution. So then 82.5% will be somewhere here. And I am asking you, what is this score? Now, if this is 82.5%, can you tell me that how much will be this area?
So 17.5%.
17.5%, exactly. That's 100 minus. So I am basically trying to find out the inverse normal. So finding out the point for which the probability will be 17.5%. Now that I do not know, and I have to use my system. Now the problem is that here I have only been told that if the probability is like this, let's say norm.df, it has been only been told to me that if it is 20, if the score is 20 and the mean is 25, then I can get up to 20 what is the probability. This I can get. But nobody has told me what will be the value here so that this particular thing will come as 12. Nobody has taught, or 17. Nobody has taught us that. So now I do not know it in simple words. So what I will do, when I do not know whether Gaurav has shown you this thing, that the blind way, if you do not know how to code, if you do not know a particular line, what to do? Gaurav has shown you lots of I would say ways to use NumPy and pandas and etc. But often you will find situations but you do not know how to code, what is the exact syntax. What will you do in that case?
Google.
You will Google, exactly. So that's what we're going to do. And what will I Google in this particular situation? So my Google is taking time to open, just 1 minute.
So you can use the tab of that edge also.
I do not know whether that will give me good, it uses Bing. I can open Google here as well, probably.
Yes.
Instead of opening another browser. So I actually do it in my computer. This is my office computer, which is a little bit slow. Tomorrow I will change it, or I will join it from my laptop. Okay. So okay, I will just put it a yes here. Okay, so let's write it down. How this is what? This is basically normal inverse, right? I'm getting, I do not in Python. And preferably norms inv. Spicy. Okay, so within the spicy package itself, it is available. Let me see. But so how to calculate the inverse of the normal cumulative distribution in Python, blah blah blah. So somebody has saying norm is, and they have also shown. Did they show the usage? Is the inverse of CDF. Norms in, they have not shown the usage here. Let me click on it. This is for standard normal. Okay, so it's called PPF. Let me find out this one. So PPF, norm.ppf is in spicy. So let's just write it down. What is my probability that I'm looking for? 0.1725, right? 17.5, 0.175. And the mean is 25 and the standard deviation is 4. Run it. This is the value 21.26. This is the value up to which. Now, if I can solve this problem, the second problem, if I check, did you get this code? First of all. And what I did is I just searched for it. I searched and read for it a little bit, and that's how I got. Now, if I want to answer the second question, the top 2.5% of the scores get to compete in a statewide history context. What is the lowest someone can get and still go to compete with the rest of the state? So basically, it is asking me the top 2.5%, what is the cutoff? So I will just change it. What will I put here?
Standard deviation 1.9.
0.975. 2.5% means 0.975. And if I run this is basically 25 plus 1.96 into 4, that value. It's 32.884 is something. So this much should be the score. Above this much or up to this much should be the, or at least this much should be the score. Then you can get to compete with this thing. So these are some of the ways you can get normal inverse. Fair enough. So that's all for distributions. We'll stop here. There are 2-3 distributions that we have learned. I will start with in the next after taking or should I go ahead, because we have not spent time. Let's, and I there was at least around 15-20 minutes break. So I will not stop and take a break now to avoid any kind of loss of time. Now, next thing that we are going to talk about is called the central limit theorem. This becomes very important.
Sorry to interrupt here, but then I'm still struggling to understand why we took 0.975.
Sure. So you see, what is the question here? The question is the top 2.5% of the sports get to compete in a statewide history context.
Oh, okay. Top 2.5%.
So when it was top 82.5%, we took
Okay.
100 minus 82.5. So if it is top 2.5%, I will take 100 minus 2.5.
Yes.
It's if we want to see pictorially, it is basically these people. This is 0.2.5%. What is the cutoff here? When the mean is 25 and sigma is 4. So this value you are asking me.
Okay.
Okay.
Yes. Thank you.
Okay. So we'll close this one. Okay. So now a thing that I'm going to discuss a little, it's a little bit difficult, but let's try to understand this. So central limit theorem says what? So you see, I have just demonstrated a little bit back that if I take a very large sample, then the sample mean and the population mean comes very closer. However, taking a very large sample, let's say 10,000, 20,000, like that, is difficult in general. So we in statistics try to make an inference about population from a small size sample. That's why this word of statistics comes in. If I could use the whole data, right now machine learning people can do that. And that's why they don't bother about statistics. They go for huge data and they just analyze the data. So in such kind of situation, when I have to rely on a little bit of fixed amount of data, let's say, or lesser quantity of data, sample information becomes very important. And what becomes further more important is how I can make an inference about the population from the sample. So given that, what kind of information that I can get? So it has been seen that if, irrespective of the distribution of the population, if I take a sample, let's say you are asking me what is the average income of the average family income of the people in this institute. So there are 20,000, I think right now 13, 14,000 students are there. And it is probably difficult to get the data for 13, 14,000 students. So I decided that every day morning I will wake up and take data of 100 students. So day one, I took 100 students data. Some data points are there, and I got a mean. Okay. So before I go ahead any further, let's set certain nomenclature. So there is two things called population and sample. Population items and sample items are written like this, xi and small xi. Population size and sample size are written like this, capital N and small n. That means this I varies from 1 to capital N. This I varies from 1 to small n. Then sample mean is written as mu, which is basically summation of capital Xi divided by capital N, while this is written as X bar, which is summation of small xi by n. So this X bar and mu is important to note. Then comes standard deviation. This is written as sigma, which is the population standard deviation. The formula of that is capital Xi minus mu square divided by capital N, and then take a root of that. Well, this one is written as S, which is this much is same. This one is X by minus X bar square, and the denominator is small n minus 1. This minus 1 comes from something called degrees of freedom. We will not go into that. It's not a stats course, but in a basic statistics course, this particular question will be an important question, right? Why that is n minus 1. Anyways, so I'm just writing it down right now because these terminologies we will use and people may get confused. So coming back to the story again. So I was sampling and I got the sample means. So these are the sample mean of day 1. Similarly, day 2, I got another sample, 100 persons. Sample mean of day 2, day 3, and so on. I kept on doing this up to sample mean of day, let's say 50. Now, if the sample size is 100, the sample size is how much here? I told the N is 100 and capital N, how much I told? Around 12K. So that's if the sample size is small, then this sample means X bar D1, X bar D2, X bar D3 will be no relationship with mu. They will have no relationship with the population mean. These values will be very different. The distributions will be very different. The actual distribution will look like a normal curve probably, and these ones will look like this and this and this and probably something like this. No pattern. Everyone will be different. However, what else then if it is everything is different, then for small samples, how will I make an inference? I cannot make an inference. However, it has been seen that the mean of the sample means, that means if I add all these things up and divide it by 50, so we call it X bar and then another bar. That means X bar of X bar. Mean of a sample mean. X bar is sample mean. Mean of multiple such sample means is X double bar, which is basically summation of X bars bi divided by I is equal to, in this case, 1. Let's say if I have done it for 500 times, then I is equal to by 500. Something like that. So this X double bar will asymptotically, means as this number goes to infinite or becomes larger, as this particular number, which is number of times you have taken this sample, as this m tends to infinite, this X double bar will tend to mu. So the sample of the mean of the sample means will be equal to the population mean. This is one thing that has been observed in central limit theorem. What else? It can be proved mathematically also. What else? It has also been seen that the standard deviation of the sample means, this one understanding is very difficult. Understand carefully. This guy will have a standard deviation S of D1. This guy will have a sample standard deviation S of D2, S of D3, S of D4, S of Dn. I am not talking about these guys. Now what I am talking about is not this sample mean of these 100 person or the sample mean of these 100 persons or the sample mean of these 100 persons. I'm not talking about them. What I'm going to talk about is the standard deviation of this column. The mean of this column is this one. This column will also have a standard deviation. So that is basically the standard deviation of the sample means. That means every day morning I take a sample mean. I get a sample mean after taking sample. If I do it for 500 days, then 500 different sample means. The standard deviation of those 500 values. We also call it a standard error in one term, which is written as SE. It has been seen that this will follow when m tends to infinite. This will follow sigma by root n. What is sigma? Sigma is, remember, population standard deviation, and n is sample size. So this will follow sigma by root n. That means what I told? I told this is basically central limit theorem. This theorem is called central limit theorem. I told that this thing that I got right now, that sample mean on D1, sample mean on D2, sample mean on D3, up to sample mean on DM, day 1, day 2, day 3. These guys, when I do a sample mean, when I take a mean of these sample means, it will follow a population mean. When I said sigma standard error, that means standard deviation of this sample means, that will follow sigma by root n. Not only that, it is also told that this sample means will follow a normal distribution if n is greater than 30, or a t distribution if n is smaller than 30. What I'm trying to say? So t I will talk about later. T has a special case. T distribution I will talk about later. So it follows a normal distribution when it is higher than 30. Now, if these three things are true, what does that mean? That means that X bar follows a normal distribution with mean mu and standard deviation sigma by root n. This exactly is what central limit theorem is saying. Now, what are the implications of it? What does this particular central limit theorem, why I'm teaching you? Let's say in one morning, I got up and I got X bar, which is the average income, to be, let's say, 2 lakhs per annum. And this exact same exercise somebody did last year, and he got us, and basically he got the sigma. He didn't do last year. He actually calculated, or from some gods, what we call in Bengali, we call it Doibobani. I do not know what God's message. Let's say from some God's message or from some past data, I got sigma as 0.5 lakhs per annum. Let's say somebody has told me, and this n was 100. Remember, I took 100 people sample, I got X bar to be 2 lakhs per annum. Then what do I get? What is the information that I get? I know that X bar follows a normal distribution with mean mu and sigma by root n standard deviation. What does that mean? That means if this is my graph of that normal distribution and this is X bar, then this is mean mu. This thing of X bar. This is mu. Then mu minus 1.96 sigma by root 10 and mu plus 1.96 sigma by root 10, this x bar will fall within this with what probability? What will be?
85%.
95%. Now let me write down some meanings of that. That means probability that my x bar will be between these values is 95%. That's what this central limit theorem tells me. Are you with me? I need an answer. From this, you didn't get anybody who does not get this particular line from this particular line. Okay, do you know that if A is greater than B, then A minus 2 is greater than B minus 2? Do you know that? If you know that, that means if I subtract the same number, the inequality holds. Can I write it like this? Can I write it like that?
Yes.
Okay. Do you know if A is greater than B, then minus A is smaller than minus B? That means if I multiply by minus 1, sign of the inequality changes. 2 is greater than 3 means minus 2 is. So let's multiply with minus 1. Fair enough? Or now I'm adding x bar everywhere. Fair enough? If there is problem in understanding, you this is 1, this is 1. Okay. Are you with me up to the last line? Anybody has a doubt? From here to here, I subtracted minus mu. Here to here, I multiplied with minus 1, and then I added x bar. So if this is the case, then I can also write mu x bar minus 1.9 sigma by root 10 x bar plus 1.96 sigma by root 10. This is 95%. What does that mean? That means with a 95%, I'm getting a confidence interval. I'm getting a range within which my population mean is existing with a 95% probability. So what is the, from this particular line, I'm getting that the mu's lower limit and mu's upper limit will be x bar minus 1.96 sigma by root 10 and X bar plus 1.96 sigma by root n. This is called the confidence interval. So this is also called basically the interval estimate. What is the interval? Did you get this calculations? Now let's say somebody told me, as I was telling, that I got a X bar as 2 lakhs when I took a sample of 100 people. And somebody told me that, you know, the population mean is 0.5. Then what will be my upper limit? This will be 2 minus 1.96 into 0.5 divided by 10 and 2 plus 1.96 into 0.5 divided by 10. Whatever is the value, I can say that the population, the actual population's mean will fall within this range. With what probability? With 95% probability. You might say, sir, the sigma, how will I know? The sigma is 0.5. It is coming from some God's message. How will I know sigma? If you do not know sigma, use S. Use S means use the sample standard deviation. And another catch, when you do not know sigma, when you are using S, when ES is being used, if sample size is smaller than 30, instead of 1.96, instead of normal distribution, use T distribution, a different kind of distribution, which normal distribution looks like this. T distribution has fat tail and a little bit high, looks like somewhere like this. It's close to T distribution, sorry, close to normal distribution when n is equal to greater than 30. But when n is smaller than 30, it has a other shape. So that's why we are generally told to use T distribution. I will talk about that in a few minutes. Now tell me, instead of 95%, if I wanted to have a 99.97% confidence interval, what would have changed in this whole story? If I thought that no, 95 is not good enough, give me the range within which the mean will fall at a probability of 99.97%.
You have to use 3 sigma by n. Sorry, 3 sigma by n.
It will be 3 sigma by n, because then this probability will be plus mu plus minus 3 sigma. If I wanted to be relaxed, if I wanted to have a 67% probability, then for 67% probability, it would have been only sigma, right?
Yes. And I have a doubt. So when you say that if we don't have sigma, we can use S. So
yes. S comes from this. This is S. This 2 lakhs, this 100 people, 2 lakhs. This I will also get a sample standard deviation, right?
but then I mean, so it should be the standard deviation of I mean, from multiple samples, or
No, it will be from one sample.
only one sample.
I'm not talking about SE. I have not asked you to use SE. SE
Okay.
will never be used basically. SE is a conceptual term. You will take SE comes from multiple samples. But practically taking multiple samples for the infinite number of days is not possible.
Yes,
Right.
but why would we then saying that, I mean, if S should be I mean, if we use S, so N should be greater than 30. So what the relevance of N here?
Okay. So let me come to that. So first of all, you understood that I have to use S, right?
Yes.
That much you understood. Now, why I'm saying that it should be to keep it normal distribution, it should be higher than 30.
Mhm.
So this you use S and do nothing, no more changes if n is greater than 30. But if n is smaller than 30, then do a small change and use t distribution. This is what I'm suggesting. Why I'm suggesting that? I'm suggesting because it has been seen that t distribution, what is the graph that I've drawn? This is normal distribution, okay? And a t distribution is a little bit more penalizing. It is fat in the side and a little bit high in this side. This is how the t distribution looks like generally. Okay, so black one is t distribution and the red one is normal distribution. Now, what this t distribution is doing in this particular case is it's more of a penalizing higher. So if you are either in this range, if you don't fall in this range, then it will push you towards this range.
Okay.
In below, the probabilities are lower than normal. In these positions, the probabilities are normal is higher than t. Normal is higher than t. So either in t distribution, either your value falls very close to the mean or they are outliers.
Okay.
This is for the t distribution.
Reason why we say 30?
So the 30 thing is that when t distribution, the shape of the t distribution varies with the sample size. As t distribution, as the sample size increases, this becomes pulls up and this become pull down. And at n greater than 30, normal and t distribution more or less look same.
This is a thumb rule.
This is an observation that has been seen.
Okay.
T distribution has a formula, normal distribution has a formula. I'm not going into that level. Those are formula. At n is greater than 30, they are asymptotically similar. So in all practical purpose, you understand when n is smaller than 30, we use t. Is n is greater than 30, t and n are same. So then use t only. Why are you using n? So in actuality, we do not use n at all. We use t only. Because n greater than 30, t and n are same. It looks exactly same.
Okay.
Now, why 30? It has a through trial and error method, this particular value has been found out.
So the T table and the N table, the probability tables that used to come with the book, they were not same, right? T table had different probabilities.
After 30, you will find out same. That's why the T table had given only up to 30 something.
Distribution, huh?
You will never see a T table beyond 30 because beyond 30, the T table and Z table are same.
So essentially, for making some idea about the population, if we have a sample of 30, we can make assumptions about the population.
No, I can make assumption about the population even when the sample size is smaller than 30.
Smaller than 30.
But this, I have to use T distribution. What happens is T distribution, this 1.96 becomes a little bit more relaxed. It becomes 2.59, let's say. Means you are spreading you are more risk averse in T distribution. You are spreading your range. Because you have less information, no? Because n is smaller than 30, you have less information. You are less confident. And because you are less confident, you are spreading up your confidence interval. Keeping the 95% probability same, you have to increase the confidence interval. Are you with me up to this point?
Yes. So why I had questions on 30 is, I mean, I was just thinking that maybe in banks or where we have transaction data, so the actual population would be a very large number, and then just a 30, will it help, I mean, doing the right calculation for us? I mean, so that from there I was asking, I mean, so why we have
I will not answer that. Be with me. So this is a different question. The question is, first of all, what I'm answering is that given that you have taken a small sample, what inference I can make? But you are asking a different question. You are asking me whether this sample size is good enough. Whether it is good enough or not depends on what inference you want to make or not. Do you understand what I'm trying to say? So if you are saying, let's say, I am trying to predict what will be the number of COVID patients in the next day. Okay, tomorrow. How many new COVID cases will be there in India tomorrow? I am trying to predict that.
Okay.
You are giving me a confidence interval. You are allowing me a confidence interval from 0 to plus infinite. I will not take a sample. I will not even look at the past data. I will blindly say that, okay, whatever, 50,000, 2,000, 100. Everything is there. Everything is okay in the confidence interval from 0 to infinite. Right? Now you say that no, 0 to infinite is too high. I will not allow that kind of confidence interval. Whatever you say, plus minus 2,000, within that range it should be. Now I have to think that what data I should take so that I can give you an estimate within plus minus 2,000. So how much you will allow me, how much relaxation, how much that plus minus you will allow me, that defines what should be my sample size.
Okay.
Okay. Now, simple calculation, what should be your sample size? You know, so if you allow me 95% confidence interval, then I know this is plus minus 1.96 sigma by root n. Okay. And you are saying that this plus minus should be, let's say, in your nut bolts case, you say that this should be 0.10. Okay, this much you told me. And what should be my sample size? Let's say if I know a sigma from past, if you have told me that in the last 1 year this was my sigma, now take the sample. What I will take is n is 1.96 square into sigma square by 0.1 square. That will be my n. You get it what I'm trying to say?
Yes. Yes.
Now, let's say you do not have this data also. Then what would I use? I will use, if I do not have this data, then this changes to S. I will take 30 data points and I will calculate some S. Okay. And then I will check 1.96 S by root 30 is equal to root n is equal to 0.1, you told me. So then n is equal to 1.96 into s square by 0.1 square. Whatever n I'm getting, if it is higher than 30 or smaller than 30 or equal to 30, I will do that. If by chance, if it is higher than 30, then I have to take, let's say this value is 36. So after doing this calculation, this value is coming to be 36. Then I have to take again 6 more observations. And now I make it 36. I get another S. Again, I calculate 1.96 S square. This is S1, let's say S2. S2 square by 0.12. 0.1 square. Now let's say this calculation, after doing this calculation, I get this is coming as 35. I have already taken a sample size of 36. I'm fine. I stop here. Till I get a sample size, which is calculated sample size, which is lower than my sample size that much I have taken, I will keep on taking sample.
Okay, so this will keep on going on.
This will keep on going on. This is the right way. we do not do in this way. In all practical purposes, we don't do in this way. We generally generally we have a past data. We calculate this, and to avoid this kind of exercise, whatever n I got, I take into 2. Because
Why into 2?
y into 2 is nothing, into 2 or into some factor. Why? Because paying a statistician is more costly than taking samples. If you ask me this particular problem, I know I'm an expert, but my time has some money, no?
Yeah.
So you would rather take twice of that sample that is coming up there rather than paying me something. That's why into 2.
Okay.
But if by chance, if it is a mission critical kind of situation, let's say patients, you're doing testing on patients, drug testing, you cannot do into 2. You have to pay a statistician for that. Okay, so that's how we do. I didn't want to cover in this course. This is a statistics concept, but yeah, that's how you decide the sample size.
Thanks.
Okay, any more question? Okay, now let's start with, I have talked about till this point, I have talked about confidence interval, how to get an estimation about the population from the sample. Now, I will do a similar thing a little bit in a different way. Sometimes we also have to test a claim about a population, test a claim about a population. Yes, Suman.
Sir, so you told at 1.96 that that variability in the confidence interval, we get it from the past data.
No.
That is 0.10.
No, 1.96 I will not get from past data. 1.96 is coming from this choice. Whether I take 95%.
Yeah, that is that choice. I mean to say, sir, that that 0.10, that is the variability of
Yes.
95% in the confidence interval. That we generally get it from the past data.
No, that I am asking you how much variability you are allowing. I am saying, asking that, I'm asking, so this particular question comes in this situation. Okay, somebody is asking me, okay, what is the population mean? Giving me an estimation of the population mean with a 95% confidence interval. However, the range will be 0.2. That means plus minus 0.1.
Okay,
So
okay.
the accuracy level, the allowed deviation, the accuracy level should be 0.1.
Okay, sir, got it. So, sir, in this case, what we can see, sir, is so the allowed level is this one. Okay, so that is the. But again, sir.
In other words, what it is saying that give me a population mean such that if with 95% probability the sample mean will fall within 0.1 of that population mean.
Within point, so it is 0.1. So it is like
value. It's centimeters. If in our
centimeter. Okay, fine. Okay. Got it. So answer again, it is n multiplied by 2. You told, sir, it is the statistician cost, or it is the statistician cost. So we increase the sample instead of employing more.
Yes. So so we call it the in civil engineering. I do not know whether you have studied civil engineering or not. We used to call that the risk, a particular coefficient, the impact factor or something like that, which is, let's say, a bridge can hold. A bridge,
yeah, that frequency level, sir, simple harmonic motion, a bridge can hold this level of this amount of persons like this.
Yeah, so let's say a bridge can hold 500 tons or 500 metric 5 million tons of weight. Let's say you have calculated and found out 5 million tons of weight the bridge can hold, but you have calculated with making an assumption about the steel quality and the cement quality and blah blah blah. So to be
Yes.
further accurate, you have to pay a lot to do getting further accuracy. Rather than that, why don't you design the bridge for 10 million tons?
Got it, sir.
While
Got it.
only 5 million tons will go on that particular bridge, you are basically planning it for 10 million tons. So the extra cost of making the bridge from 5 million to 10 million will be much lower than getting the exact value.
Got it, sir. Got it.
Okay. So sampling is less costly, but here the same thing will not be possible, as I was telling, if it is, let's say, drug testing on human patients.
Okay, that won't be possible because
That will not be possible because it's more costly to recruit human people to try on a drug
testing. Right,
than a statistician who will find out things properly.
Okay, got it, sir.
Okay.
Thank you, sir. Thank you.
Okay, so next is testing a claim about a population from a sample. So how I have already told this much, I have told you. So somebody is claiming, let's say, that I make thousands of nut bolts and my mean is let's say 2 centimeter. Then what is the alternative hypothesis? Mean is not 2 centimeter. Anything very high from this 2 centimeter, let's say 3 centimeter, or 4 centimeter, or 5 centimeter, there is a problem there. And anything very lower from this 2 centimeter, let's say 1 centimeter or 0.5 centimeter or 0.25 centimeter, there's a problem there as well, both sides. So to test that, what do? I try to find out what is the upper limit and lower limit of my X bar. So remember the probability that if this was true, the probability that mu will fall between this range and mu will fall within this range is 95%. So if this is true, I will get 95% of my X bars here and only 0.25% of my X bars here. So if I say, let's say the X bar is falling here and I am saying that this is wrong, then I am doing a mistake what percentage of time? So when this is correct, understand this, what I'm saying. When this is correct, the probability that X bar will fall beyond this range is only 2.5%. Now I'm saying that the moment X bar falls here, I say this is wrong. This strategy is an erroneous strategy, is a mistaking strategy. How many percentage times? 2.5%. So if I take a strategy that whenever X bar falls outside mu plus minus 1.96 sigma by root n, reject null hypothesis, I am wrong how much time? 2.5%. I'm wrong basically 5%. No, sorry, it's 2.5. I have told wrong. It's 5%. So I am wrong 5% times. The moment I take a strategy like this, I'm wrong 5% times. Now, why I'm choosing this? Because I'm allowing myself to do this 5% mistake, because I am correct 95% times by doing this. So that is a hypothesis testing kind of a method. I find out the upper limit and lower limit, and beyond that upper limit and lower limit, I reject my null hypothesis. By rejecting the null hypothesis, I'm correct 95% of times, and I'm wrong 5% of times only. Now you see, if I am wrong 94% of times and if I'm correct 94% of times and wrong 6% of times only, I'm not even allowing that. That is my level of, I would say, conservativeness, that even if I am not shifting it to a little bit here and allowing 1% more, I'm not doing that. I'm keeping it 95%. Now, some person can be further more finicky. Some people say that no, 95% times correct, 5% times wrong. That is problematic thing. For example, let's say based on this, you are trying to decide that whether you will do a fine to this person or not. Let's say you have been given an order that you should make your nut bolts of 2 centimeter. You are saying that yes, we are making 2 centimeter only. The client got angry. Client told done a civil suit against you. Client told that no, they are not giving 2 centimeter. They are telling it false. So the court said that prove it. So the client hired a statistician, and client took a sample. And by taking the sample, it is shown that that sample mean is coming beyond 2 plus minus 1.96 sigma by root n. So client proves in the court that your null hypothesis that mu is equal to 2 centimeter can be rejected. Now, for a client who is doing a business, plus minus 1.96 sigma by root n can be a good confidence interval. But so 95% confidence interval, or this is called alpha, this is called type 1 error, alpha is 0.05. It is okay for your client. But this much of error, this big, now what you are asking, client is asking to penalize the supplier. Now, based on that 5% error rate, this guy cannot do that. The court cannot do that. Court says, no, I cannot do that. Why don't you give me 0.03% error rate? I cannot go for 0.5%. It should be 99.97% within the range and only 0.03% outside the range. Then I can probably penalize. So then what? How the whole story changes? You do Pu minus 3 into sigma by root n, x bar P plus 3 into sigma by root n is 99.97%. You find out whether x bar is within this range or outside this range. Is x bar is outside the range, reject null hypothesis. Reject null hypothesis. And by taking this strategy, how much time you are wrong? 0.03% wrong. Still, if it is coming that you are outside this range, then the client probably will win the case. So this is how we sometimes take decision that whether to follow. Now, why it is t-test? Why we call it t-test? The moment the sample size is smaller than 30 or the sigma is not known, we use S instead and we use t distribution instead. That's why this particular thing is called t-test. When we are using normal distribution only, we call it z-test. Otherwise, we call it t-test. Now, there are different ways of doing this. This is one way, which is finding out upper limit and lower limit. Understanding this is very easy. Another way of doing this same problem is finding out the p-values, which the computers do. So now you will be doing this in computers, so you have to understand what the computers are doing. So I will quickly try to show you what the computers are doing and what the p-value means. So you see, I again told I am testing that whether you are giving me a 2 centimeter wide this thing or not. So this was my range 2 plus 1.96 sigma by root n. Sorry, this side it is minus. This side it is plus. In this range, I would have accepted. Outside this range, I would not have accepted. Let's say I calculated X bar and X bar came here. Now, if this is the X bar, let's just draw it once more. Let's say I got some X bar value. And that X bar values corresponding CDF, this particular value. Or if the X bar has come here, then this particular value or both the values together. Let's say X bar I got as 4 centimeter. So X bar is 4 centimeter. This is 2 centimeter mean. So this is 2 centimeter this side. So this part is 0 centimeter. Oops. This part is 0 centimeter. So these two values together, this side and this side, these two values together, let's say you got the probability to be, these two values together, probability to be, let's say, probability of the black area is, let's say, 0.03 or 3%. Can you tell me from this information whether X bar falls outside the range or inside the range of mu plus minus sigma by root n? Both sides together, the area is 3%.
For 2.196, the both sides outside the area would be 5%.
5%. This area, this shaded area is together, this is 2.5%, this is 2.5%, together it is 5%. And here I am getting together it is 3%.
So it is
Is it-
outside.
Is it outside or inside?
Okay, sorry. So 3%. So it will be. It will be within the 5% area, but the point is it will be outside of 2.
It is the outside of 2 plus.
Outside of 1.96.
Exactly. So this is outside of, because up if it is 3%, then this side is 1.5%, this side is 1.5%. So to make it 2.5%, this will be the range. It will be outside this range. Anybody has a doubt what I'm saying? Please let me know. Unless you let me know, it's a magic box that is going on. So if I can calculate that p value, I can also say that whether I accept or reject the null hypothesis. So thumb rule is when p is smaller than 0.05, null will go. What is the p? P is basically the probability that I am doing a mistake and the null is correct. I'm doing a mistake by rejecting the null. That probability is this p-value. As long as the p-value is lower than the allowable mistake 0.05 is that alpha value. That much mistake I'm allowing. As long my p-value, the calculated p-value is lower than the allowable mistake, I am fine. I can reject the null hypothesis. So that's how we do the comparisons. Now in t-test, there are 3 types of t-test. We will quickly talk about these 3 types of t-test. One is one sample t-test. One is 2 sample t-test. And another is called paired sample t-test, which is also one kind of one sample t-test. Let me help you understand what is one sample t-test. Let's say I am trying to say, my claim is the average rating of my students in the class is exactly 4. This is my claim. To do this, to check this claim, I take a sample. How many samples will I take? Only one sample I will take of sample size, let's say 40 or 50, whatever. But the number of time I will do the sampling is only 1. And I am comparing with a benchmark, which is I'm telling that the benchmark value is 4 compared with that. So that is called a one sample t-test. Whenever you are comparing with a benchmark, an external value that has been given to you. For example, here mu is equal to 2 was an external value. It has been given to you. And you are comparing with that benchmark. However, sometimes we compare between two groups. For example, let's say my claim is I teach statistics in let's say here, and my claim is that section A and section B likes me equally. That means my average rating in section A and my average rating in section B are same. So what is my claim then? That mu of A and mu of B is same. Here, what is the claim? Mu of A is some benchmark. So here I will take two samples, one from section A and one from section B. Paired sample says that, let's say I'm saying that in the paired sample, in one sample or in two samples, the two samples are independent to each other. The people I'm taking from sample A, section A, and the people I'm taking from section B are not related. But in paired sample, they're related. Let's say I'm saying that Swachh Bharat Abhijan, this particular campaign, has increased the cleanliness of the states. So we have, let's say, 29 states right now, 29 or 28, forgot. I cannot take all the states data. I took 10 states data. Now I have to, if I want to do a before-after comparison, before campaign and after campaign comparison, I have to compare with same set of states. I cannot compare West Bengal with Manipur or Telangana pre versus Sikkim post campaign. I cannot do that. I have to compare Sikkim pre-campaign, post-campaign, West Bengal pre-campaign, post-campaign, Jharkhand pre-campaign, post-campaign. That means my first sample and second sample will be one-to-one mapped. That is called paired. So these are three different types of things. Paired sample, if I say that mu A, mu after and mu before are same, or mu after and mu before plus 5, instead of saying that, I can also say mu after minus mu before is equal to 5. And then I can use this as a variable and do one sample test. So this basically can be written as a one sample test also. There is another way of solving this, breaking this. One is called one-tailed and one is called two-tailed. Two-tailed tests are tests where the null hypothesis has an equality sign. So I am comparing whether it is equal to a benchmark or whether it is one group and another group are same. But one-tailed test talks about inequality. For example, here it is whether my sample is higher than the benchmark. So the students' rating are higher than 4, or section A is higher than section B. In such kind of case, only one side I'm doing the test, and that's why we call it one-tailed test. I will quickly show how these are implemented in our Python. So I've also shared with you, just 1 minute, another file which is within hypothesis testing. You will see this notebook. So for that, to run this, you have to run this bioinfo kit. I'm not sure whether this is already installed or not. I will run this one and check. If it is installed, then I will not require. If it is not installed, make it a comment and then install it. So what I'm running here, from spicy, I am importing stats as ST. And from bioinfokit, I am importing get data. Basically, I'm reading this data. You can read from data. If the data is saved in your computer, you can do it by read.csv. Okay, no module called bioinfokit. So this is not installed in this system. In my home computer, it was installed. So I asked it to install now. Let's just wait for a minute.
So could not install in my laptop. So it's giving an error, could not fetch URL.
It's giving
An error where it's saying could not fetch URL https py.python.org and something. So I don't know.
just 1 minute. Who is this? Who was speaking?
Okay, Syandit, I was speaking. So
I will let you share the screen.
no, so basically the video lecture and the this thing Python are on two separate machines.
Okay, okay. Okay, means is it computer connected? Means internet connected, that machine?
Yeah, it is internet connected, but I think it is. I can share a screenshot. But where?
Yes, you can otherwise share it later as well.
Yeah, I know.
Okay, so mine is installed and then I'm running this line right now. So this, I'm just read a data set, and the data set's first two things I just read. So it has some value, some size value, doesn't matter. So there, so if I just want to show you the whole data set, df.shape. So there are 50 rows and one column. And what are those 50 rows? Let's just show it quickly. So some values, okay. These are sample. And I'm asking that whether this is the my null hypothesis is H naught, we call it, is that the population mean is equal to 5. I'm testing that whether that is true or not. So I'm saving it in one array and using that array for. So when I run it, the result, the p-value that I'm getting is 0.714. 0.714. So you just see what is the mean of A that I'm getting. You see, if I have to calculate it manually, A dot mean is 5.05. And if I print A dot mean plus 1.96 multiplied by A dot SD, and then minus 1.96 A dot SD divided by, okay, square root of 50. So 7, let's say write 7. Okay. 7. So I have to import numpy. What is happened? STD? What was standard deviation? STD, no? Yeah. So you see, this was my, okay, not this one. Sorry, just wait. This will be 5. This will be 5. This was my upper limit and lower limit. If X bar falls within this range, then I can say that the mean is correct. The null hypothesis is correct. Otherwise, I will reject null hypothesis. And what was my X bar? My X bar was 5.05, if you are not wrong. So my X bar was 5.05, which is well within this range. So I cannot reject the null hypothesis. Similarly, here I'm getting P is 0.714, which is not smaller than 0.05. So I cannot reject null hypothesis. What is my inference? That my population mean is actually equal to 5. I cannot reject it. I do not have enough evidence to reject this claim that the population mean is 5. Now, same thing if I'm doing it for another case. Let's say here I've read another data set which has two gene types. So let's just read the whole data set itself. So some did, okay, so not head, they have df.shape. Let's just read this first. So there are 12 rows and 2 columns only. And if I just this thing, all the 12 rows, these are my 12 rows. Some A's are there, some B's are there, and the yields are there. What is my hypothesis? My null hypothesis is say that A is equal to B. So then what will I do? I will do all the A, just check df.log. df.log, that means df.location. Which one? The yield column. So take the yield column. How I will take the yield column? Such that take only such rows where genotype is double equal to A, and here genotype is double equal to B, and then convert them to arrays, basically numpys. So I am running that. Okay, so 2 numpy I can remove. I can run that, and A or B are created. Now I'm doing an individual t-test. A is equal to A, B is equal to T, and I'm doing equal variance is equal to true. This one I am not going into details. So anybody who wants to know should study a little bit this statistics in a greater depth. I will share a book's name. You can study that. But in all practical cases, we will keep this equal variance equal to true as our assumption. Now, no, actually equal variance is equal to false as our assumption. Why will I say true? Now, let's say if I do that, my p-value I'm getting is 0.0003. That means it is smaller than 0.05. What was the null hypothesis? Null hypothesis was mean of A is equal to mean of B. This was my null hypothesis. My alternative was mean of A not equal to mean of B. The moment I get a very small p-value, this null hypothesis can be rejected without any kind of mistake. So I can reject this null hypothesis. So I'm just saying that mean of A and mean of B are not same. Why? Why I'm saying that? Just check the mean of A and B. A mean and B mean. What are the values? So A mean, just minute, and B mean. If I write print for both of them. So for gene type A, the mean value is 79, and gene type B, it is 89. There are quite a bit of difference. It's not very same. And if I also say, let's say A dot std and B dot std, the standard deviations are okay. How will I?
Second one, you have put a dot between mean and standard.
Okay, got it. Thank you. So you see that 79, if the mean is 3.3 plus minus plus 2 into 3.3 is 6.6. So the highest value in the confidence interval is 79 plus 6.6, which will be around 85. And here the lowest value is 89 minus 6.6, 83. So the overlap is very small. So that's why they are saying that they are not same. The p-value is coming such a low value.
And why do we have this A equal to A and B equal to B in the t-test syntax?
Okay, so it is just saying that, so just let me just check. If I remove that, it should run rather. So you have to check probably this syntax. If I'm not wrong, those are defined as A and B. And those in the code, these particular variables have been defined as A and B. I'm opening the manual. See, A and B is the parameter names. That's how they have defined it. So it's not our choice.
Okay.
So you can name something else. Let's say you can say A, B, C, D and E, F, G, H. However, the problem is if you write A, B, C, D, E, F, G, H here, it will give you an error. But if you write A equal to A, B, C, D and B equal to U, F, G, H, you will get a result.
Okay, so basically A and B are something defined in this.
Defined within this function, whoever wrote it.
Okay. Okay. And same with me. I mean, in fact, I am also getting an error while installing this bioinfo kit.
Okay. And can you share your screen?
Yeah, I can.
Okay. Let's try to share it. So we'll close it here. There's nothing more to go on t-test. We'll talk about 2 more tests tomorrow, and then we'll go to regression.
It's not allowing me. So it's saying host disabled participant screen sharing.
Just 1 minute. So I'm stopping the recording now.